So now we move to French Alps. Edmond Boyer is coming from Grenoble, from INRIA, and he's a specialist of virtual reality. He leads a team on the capture and analysis of movement, and this is what he will present today. And as you may have noticed, we have used his very nice picture for the poster of the day.
Okay, thank you for the introduction. So I'm a researcher at the INRIA in Grenoble, where I lead a computer vision group. So I'm a computer vision expert, right? And I will talk about how we do capture shapes in motion with computer vision systems. So it's not specific to sport. It's related to any kind of moving shapes. But obviously there are applications in sport. So what is the goal of the work I will present? It's to capture or record moving shapes in 3D and over time, and we call it 4D modeling. So there are other terms for that, but I prefer saying 4D modeling, which is more explicit. So the motivation is pretty much the same as with 2D recording, where you want to replay basically things, except that there is a major difference with 4D modeling. It's the fact that you have the ability to change the viewpoint, which is a very strong difference, right? So as you record in 3D, you can change and you can turn around objects. So the applications are most video-based applications, obviously, where you want to replay, analyze motions. With the additional ability I mentioned before, so the free viewpoint ability that can be used by all these new devices that you have, like head-mounted display. But you can even use that with a 2D phone, right, where you can turn around objects. So I will show an example about that. So this is the context. I'd like to talk about the historical background because I think it's interesting. So using pictures or using images to infer information about motion is not new. I guess you know this image. But anyway, I love to see this is the first motion capture system ever, I guess, right? Where so people were using images to really capture the way humans were moving. So in terms of evolution, so this is early use of image to infer information on moving shapes. And then you have the Mocap System. So the Mocap System are using markers. I guess you all know those systems, right? To infer, again, information about moving shapes. And what is very specific to Mocap System, so it's related to the fact that markers provide only sparse information about motion, right? And so you don't get information about shapes or about their appearance with Mocap System. They're quite successful anyway, right? It's not a criticism. A more recent system is the Kinect System, which was kind of a breakthrough in vision in some sense. So the Kinect System is using a different modality. So it's using a depth camera, whether it's a time-of-flight camera or stereo system, doesn't really matter. But it's using depth information from a single viewpoint to infer, again, information about moving shapes. In the case of the Kinect, so what you get is a pose, basically, at each frame. And you get slightly more. So it's a pose in terms of skeleton. So you have the joint position. And with the most recent Kinect, you get slightly more than the pose of the skeleton and the joint. You get also the orientation of the limbs. But anyway, you still don't get information about the shape itself or its appearance. And this is what I want to talk about. It's 4D modeling. So 4D modeling is slightly different. So we're using multiple videos as input. And so what we're getting as the output, it's what you have on the right. So it's a 4D representation. And so it encodes information about the shape itself, but also about its appearance, right? And it's really a graphical model. You can think of it as a graphical model over time. And so the composition here, so as I said before, the 4D model is composed of shape information. So the shape information, it's basically a 3D mesh over time. So it can come with motion information or not, depends on how much process you're doing after that. But you have also the appearance information in addition to the shape information. So this is what a 4D model is composed of, right? So you have the geometric information, which is a 3D mesh, So it's vertices connected by triangles, basically. And over that, you can map texture that is captured again using these multiple images as input. So about the technology, so we have a startup at the INRIA that sells the capture system. And this is a typical example of the capture system. So we start with the images, we extract the silhouettes in the image, and from the silhouettes and the images, we do compute, we do estimate geometric information in space. And so we will see a 3D model. And then also from the images, we can extract the texture information. So this is the way you can see that this is really a graphical model. And so we can turn around. So this is the ability you have in addition to the 2D traditional ability. You can really look at the model from any viewpoint. This is really one of the benefits. So here we're looking at it in 2D because it's a screen, but you could look at it using a HMD display, any 3D devices, right? In terms of platforms, I'm showing this platform because I think it's interesting. So just to illustrate the fact that Microsoft is interested, but not only Microsoft, but this is a good example anyway. So this is the Microsoft platform. So they have now several commercial platforms all over the world. There is one in San Francisco, one in London, recently installed in London. So they do similar things, and you have the process there. So they do estimate point clouds in space, 3D points in space. And again, to show the fact that, well, you can turn around. So this is why the models are turning around. It's really to show the fact that you can look at the models again from any viewpoint. And so from these point clouds, they do extract surface information. So it's a mesh there. And it's pretty, so one of the interesting things with the system, I forgot to mention that, it's the fact that so they're using both an active and passive system. So what do I mean by active and passive? So a passive system is a regular color camera, right? An active system is a system where the camera is sending some kind of signals towards the scene. So a time-of-flight camera or an infrared camera would be an active camera. So in their case, they're using a combination of both systems, right? So they're combining both color cameras and infrared cameras, and so they're getting a pretty precise model. And if I can, whoops, yeah. So over which you can obviously again map the appearance information, which is the color information. So we have also a platform at the INRIA Grenoble that is called the Kinovis platform since 2015. So it was an Equipex project, so it was funded by the French government, and it's a pretty big platform. So it's equipped with 68 color cameras, and one of the characteristics that is very important with this kind of platform, it's the acquisition space. So it's the size of the space where you can capture information. So in our case, it's a pretty big acquisition space. So it's almost 8 meters by 4 or 5 meters. So which is bigger than the Microsoft platform, for instance. So this is a typical example of the kind of scene we can capture. So you have the 68 videos on the left, and you have the captured scene on the right. And this is the size of the dynamic scene is really important because it means that the information you're getting in the image per character is quite small in this case because we have several characters. So we have only few pixels per character, and we are doing the reconstruction using only few pixels. So this is a very interesting case here with this kind of big scene. This is another interesting example because we are talking about sport. So this is a fast motion. It's captured at, I think it's 50 Hertz. And so you can see the model on the right. And it shows also, I think, a strong advantage of this kind of capture system. So it would be really difficult to generate this kind of motion artificially. even if in computer graphics they are doing fantastic things in generating artificial motion or artificial bodies, this would be really difficult to generate artificially, especially if you look at the way the clothes are moving. That would be really difficult to generate anyway. So for me, the message is the fact that it's pretty much, it's easier to capture this kind of information instead of, generating it. Okay, thank you. I don't know if I have, whoops. Thank you for your attention.
Thank you very much for this very nice talk, very complimentary to the previous one. Any question? Yes, I'm coming upstairs. I think I'm sorry, but we need it because we are live on YouTube, so otherwise people won't hear your question.
I don't ask my question anymore. How much it cost?
That's an interesting question. What exactly?
This, if I want to use that in a rehab department,
yes,
is it feasible?
No, there are different things. So whether you want to buy the full system or whether you want to buy models, which is different. It's pretty much like a Mocap system. You can buy the system itself or you can rent a studio for a few days.
No, the question is there some derivative of this system which could be used in what is called in French médecine physique et réhabilitation, in rehab department, to provide a feedback to the patients so they see what's wrong?
Yes, you can build a system. Would it be a real-time system in your case?
It need to be a real-time system. Yeah, for patients it will be.
So real time, it exists also, but real time is more challenging, obviously, right? Yes, you can. I think the prices doesn't make any sense. It depends on the number of cameras. It depends on many parameters. So it would go from 50K to €500,000, right? Really depending on how many cameras you would put.
And you don't know any of this application in any rehabilitation department, actually? Do you know anybody who has tried that?
In rehabilitation?
To provide a feedback?
No, I heard about it, but I don't know any. I don't have any application in my case in this direction. No, but there might be.
I never heard of it. That's why.
Well, I saw research works in this direction, but no applications yet.
But that's a problem. You see, that's the main problem. There is always nice things, and it looks like the only people who know how to bring that in the field are the video game industry. I don't understand why.
But we would be happy to collaborate, right?
No problem. Okay.
And we're not collaborating yet with the video game industry, so but we're collaborating with Microsoft.
Okay, so we hope that this day will be the beginning of a new collaboration. Any other questions? No, I'm coming, Thierry.
Do you acquire interactions between people? For example, if you have the two dancers, if they tie their hands, what happens if they after?
No, we do. Yes. So we do model shapes independently of what shapes are. So it means that if you have several people, they will all be modeled as a single shape, unless you have additional information. So, but we can anyway have prior models, and then we would model persons independently. But in practice, directly, it's a single surface with different components.
Thank you.
Any other question?
I was wondering about the precision of the little movement, like hands or feet movements. So, do you have a number, an ID of that?
Yeah, well, this is a very good question. It's related to the precision is related to the number of cameras and to the dimension of the acquisition space, right? So it's a percentage of the acquisition space. So it means that if you reduce a lot the acquisition space, then you get high precision on even hands. But if you're looking at a large acquisition space, then you have issues about precision. But we still recover fingers if it's the message. So I think that it's it would be a few millimeters the precision we're getting so far yet. We model the face, so you can see the face, and so pretty easily. And well, we're still working in terms of precision, so this will increase anyway.
Let's thank the former speaker again.